Hello, Swansea University. My name is Kian, and today I'm going to do my research presentation, which will be taken out over the summer. I'm doing my Masters in Data Science, and my research is a quantitative comparison of manifold and remote sensing clusters in China. So we'll be creating an interactive diagnostic framework and comparing different manufacturing regions in China. So, starting with the context and the goals. So, on the screen you can see that I've got the structural and remote sensing data. So the remote sensing data is satellite data, so that's just the way how the Earth looks from space. So just look, you can use it to look at different regions, see how they differ, and we're comparing it to the structural data. So those are the different components and the attributes which an area has. So things like the total lengths of roads, things like gyms, leisure centres, universities, and total amount of manufacturers. We'll also going to be looking at the spatial connectivity of the region. So let's say we're looking at, I don't know, somewhere in the middle of the map, and we're comparing it to the outskirts. So the spatial connectivity is how well that is connected, so the infrastructure which it has, so the amount of roads, railways, that sort of thing. So we'll be using different metrics to look at how well that is connected. So you may be asking why this actually matters. I mean, depends what you're looking to do, but at the end of the day, people who work in e-commerce, so supply chain analysts, they'll be able to use this to identify regions where there is better infrastructure, so they'll be able to find areas where they can find manufacturers which have more reliable infrastructure, so fast delivery times, which in return will result in lower priced products for the consumer. Also, potentially, investment bankers could use this, so people who work in market speculation, so they'll be able to find regions where there's undervalued companies, and those undervalued companies are in an area where there's a lot of infrastructure, but for some reason they're priced in lower than what they actually should be. So, this is broken down into two main research questions. So, does the structural and the remote sensing clusters reveal something meaningful on a shared grid, and can visualisation actually support analysts in identifying concordance, which is the agreement and the divergence and instability. So when I say instability, I mean how do the results differ between different runs. So let's say you've got a sample of data and you split it up into 4 parts. Using those 4 different parts, is it going to be meaningful and reliable across those 4 different splits of data? So the main way I'm going to see if the first research question is successful is when you look at the 2 different maps and you split between the spatial, the remote sensing, and the structural data, is it actually going to be concordant, consistent across the different representations? If it is, then that is something which is worth looking into. That's a region which is worth looking into further. In regards to the features, so when I say the local features, so let's say we're looking at Bristol and Cardiff, they're quite close, but places like Bristol and Manchester, they're not as close, so you want to look at the more global overview of them. However, structurally they're more similar than Cardiff and Bristol, Manchester and Bristol are, for the pure fact that they're structural features. So things like their airports, universities, gyms, they're more similar. They're both major cities. So in regards to the research gap, so I've done a lot of research for this, and you can see on the screen that we've got the China satellite data as well as the clustering. So we're going to be using a clustering method called HDBSCAN. So that's a density-based clustering. Clustering is used to find regions which have similar sort of data. So when we're looking at the different regions in China, are there different areas which are going to be in the same cluster? So like I mentioned before, Manchester and Bristol. So they're quite similar. So that's the way how we're going to group them together. So with that as well, so manifold dimensionality reduction is the most colourful one on the screen. So manifold is a non-linear way of dimensional reduction, which is abstraction, which I'm sure you're all familiar with. So that's a way of removing noise from data. So when you extract noise, so when I mentioned before, you've got gyms and leisure centres, they're quite similar. You don't need both of them, so we're able to actually extract the less relevant information. So I've got 4 main requirements for my project, which is to create a shared grid, local diagnostics, global diagnostics, and an interactive framework. These are papers which you're more than welcome to have a look at, but in essence, a lot of the papers which I've read so far, they do cover some of my requirements, but none of them cover all 4, and that's the reason why I wanted to do this research, because I wanted to actually create a framework where you can look at it locally in a small area, globally, and actually interpret it and make it be understandable, identify the right regions which are actually consistent with what you're trying to find, whoever you may be. So in regards to the visualization, so this is just a very, very brief explanation of the sensors and the radars which I'm using. So first nighttime lights is a sensor. Basically, industrial areas, they'll show up brighter, more dense, more light. And then Sentinel-1, it has 2 different radars. So it has VV, which is better at detecting flat, simple surfaces, which is represented by the squares, and then BH represents more complex things, such as vegetation, or, I don't know, graveyards. That's all I can come to my head. And that's represented by the waves on the screen there. And then I've also got a way of the structural representation of the dimensionality reduction. So PCA, which I'm sure you're all aware of because it was in one of our modules, is a linear dimensionality reduction. So it projects along the linear axis. However, the reason why we're using UMAP, which is the manifold-based nonlinear dimensionality reduction, is because PCA may actually ignore some of the nonlinear structures. Yes, we could use the kernel trick. However, UMAP is designed to preserve the local features. PCA is better at keeping the global, but UMAP finds that balance, as well as for the fact that UMAP is able to preserve the local neighborhood structure and represents the cells into clearer clusters. In regards to the diagnostic visualization, there's quite a lot going on the screen. In essence, this is purely just illustrative purposes. Only the colors represent the different clusters. The main things which I want to highlight is this rectangle, there's squares, triangles, and circles. So the circles show areas where there's not really much happening, so that's like rural areas, so there's not really any industrial activity. Urban areas, so where there's a lot of industrial activity, would be shown by the squares. So that's the spatial consistency, so that's local indicating of spatial association, which is abbreviated to LISA. And the circles are just kind of like outliers, so let's say it's just a random manufacturer just put down in the middle of the desert or something. That would kind of be an outlier, that would be one of the triangles. On the grid, you can see that I have got the black square with the blue inside. That is a selected grid cell. There is a breakdown of that particular region. It's purely just illustrative purposes only, all the numbers and that, they don't really matter, they're just random numbers I put in there just to show you that this is what I'm going to create at the end of it. And yeah, so you'll be able to inspect a certain region, then you'll have the overall global breakdown of what's going on. So you've got the agreement between both grids, so looking at the whole picture, the stability between the runs, and the spatial consistency. You'll also have the ability to zoom in, zoom out, highlight, as well as select certain features which you deem more important. So if an analyst isn't looking for features which are important, they can just remove them. So to finish up, the feasibility and the risk. So this is a big project, as you can tell, there's a lot which I'm trying to get done, and I've got a detailed timeline of everything. I mean, you can look at it, but at the end of the day, we're about halfway through thus far, I would say. And we have so far done the technical setup, the database, data ingestion, and the feature engineering is what we're working on right now. After that, after the exam period, we will be finishing up the clustering and the modeling, as well as the diagnostics and the visualization. There are 2 main risks. I mean, there's loads of risks at the end of the day, but the 2 main risks which I think are the biggest ones which could ruin this project are the write-up taking longer and the visualization taking longer. My main mitigations is using reusable templates and a design and make sure that my design is locked in early and that I prioritise the core figures and chapters. So, if you've got any questions, feel free to ask now, but remember the key question is not which clustering method wins, but which is most trustworthy when representations diverge. Yeah, thank you. Yeah, so the grid which I'm going to use is 25 kilometers by 25 kilometers. Overall, that would break up China into 24 separate regions.
Any reasons for that?
It's because if I go any higher than that, so let's say if I went into 10 kilometers by 10 kilometers, then I'll end up with 150,000 different grid cells. That will require a lot of pre-processing because every grid will have a breakdown of the local diagnostics. So when I say the local diagnostics, so every grid will have to have the computation power, the dimensionality reduction, as well as the clustering and all that. It will take a lot of time and it'll just be a bunch of noise. So when you're actually looking at it on the visualization here, it will be very laggy. You won't be able to get any meaningful data and people will get fed up with trying to sift through all of those. So I found that the best balance would be 24,000, which is 25 by 25 kilometers.
Is there any sort of